In this video, we're going to be talking about integration of rational functions by partial fractions. At this point in time, we can integrate some rational functions using U substitution or trigonometric substitution, but these methods do not always work. Our next method of integration allows us to express certain rational functions as a sum of functions that can be integrated using methods with which we are already familiar. That is, we cannot integrate 1 over x squared minus x as is, but it is equivalent to 1 over x minus 1 over x minus 1, which we are able to integrate. Example 1 says our goal is to compute the indefinite integral of x minus 7 over x plus 1 times x minus 3 dx. Now, before we do that, let's go ahead and answer part A, which asks the indefinite integral of 1 over x plus 1 dx. So in this case, what I'm going to do is I'm going to use U substitution. I'm going to let u equal x plus 1. Then du is going to equal dx. So this integral is equal to 1 over u du, which is equal to the natural log of the absolute value of u plus c. And then we can sub u back in to be natural log of the absolute value of x plus 1 plus c. So that is our answer for that part. Part B wants us to simplify these two fractions. So what I'm going to do is I'm going to find a common denominator, and in the first fraction I'm going to multiply by x minus 3 over x minus 3. And then in my second fraction I'm going to multiply by x plus 1 over x plus 1. So this is going to end up giving me a common denominator, so I'm going to combine the numerators into a single fraction, where my denominator is x plus 1 times x minus 3. And if you go about simplifying the numerator, if I distribute in this 2 and this minus sign, and then I simplify, my numerator is going to end up equaling x minus 7. And my denominator is x plus 1 times x minus 3. Now, is that a coincidence? Absolutely not, because notice that this expression is our original integrand. So that means for part C of this example, I'm going to be able to take my original integral and I'm going to rewrite it as the integral of 2 over x plus 1 minus 1 over x minus 3 dx, and I'm now able to split this up into two different integrals. I'm also going to factor out the 2 from my first integral. And from this stage, I can integrate. From earlier, we already solved this integral, so we have 2 times the natural log of the absolute value of x plus 1 minus the natural log of the absolute value of x minus 3 plus c. And there's our answer for example 1. Example 2 wants us to compute the indefinite integral of 10x minus 31 all over x minus 1 times x minus 4 dx. So part A is having us simplify these two fractions by finding a common denominator. And so my common denominator will be x minus 1 times x minus 4. And then my numerator, I have 7 times x minus 4 plus 3 times x minus 1. And then if I distribute the 7 and the 3 inside of our parentheses, that's going to give us 10x minus 31 after simplifying. And then our denominator will be this. So, notice again that this is the same thing as our integrand right here. That means that I'm going to be able to take my integrand and split it up into two different fractions like this. And then from there, I can split that up into two different integrals. I'm going to factor out the numerators from both of these. And now we can integrate. And there's our answer for example 2. The previous two examples were nice since we were given a different expression of our integrand beforehand. But what about when that's not the case and we're not given what our integrand breaks up into beforehand? It's clear that the key step is decomposing our integrand into simpler pieces. So how do we do it? The next example outlines this method. Example 3 wants us to compute the indefinite integral of some rational function here. Notice in this example, we're not given what this breaks up into ahead of time. So I'm going to go ahead and write my integrand, which is x plus 14 over x plus 5 times x plus 2. And as we saw in the previous examples, our goal here is to split this up into two fractions. One that has a denominator of x plus 5, and another one that has a denominator of x plus 2. And I don't know what the numerators are, but as we saw in the last two examples, they ended up being some constants. So I'm going to label the numerator in my first fraction capital A, and then capital B as the numerator for my second fraction. And now what we have is a rational equation, and I'm going to use what's called the method of clearing fractions. In other words, I want to get rid of all of the denominators, and so the way that I'm going to do that is I'm going to multiply my entire equation by the least common multiple of all of the denominators. And in this case, our least common multiple of all of our denominators is x plus 5 times x plus 2. So I'm going to multiply every single term on both sides of the equation by x plus 5 times x plus 2. If I do that, and if I multiply that through, the resulting equation that we would get is x plus 14 is equal to a times x plus 2 plus b times x plus 5. And now what I want to do is I'm going to distribute my capital letters into my parentheses, and that's going to give me ax plus 2a plus bx plus 5b. From here, I just want to rearrange the like terms. So I have ax plus bx, and then plus 2a plus 5b. The last thing that I want to do is I want to factor out x from these two terms. And then I'm just going to group 2a plus 5b together. And I'm going to copy these down, so I have x plus 14. Now, this is an equation, which means both sides of my equation are equal to each other, and the method that we're going to use here is called the method of comparing coefficients. And it's called comparing coefficients because that's exactly what we're doing. We're going to compare the coefficients. Notice on the left-hand side of the equation, I have a single x term. And if it's helpful for you, we could put a 1 here so that that is our visible coefficient for x. So here my coefficient of x is 1, and then on the right-hand side, my coefficient for x is a plus b. And then on the right-hand side of the equation, I have the constant term 2a plus 5b. And on the left-hand side, my constant term is 14. So let's just reiterate. A plus b here is our linear term, or the coefficient of x. 2a plus 5b is our constant term. And then on this side, 14 is our constant term. And then here, 1 is our linear term. And so we're comparing these coefficients, and what you get when you compare them is because they're equal, we end up getting a system of equations. So I went ahead and I copied my two equations down, and this is, again, a system of equations, and more specifically, this is a system of linear equations. So typically when I teach my algebra classes, there are 4 ways that we can talk about in order to solve a system of equations. There's elimination, substitution, graphing, and then guessing and checking values. I put the 4th one on this list because that is something my student said this morning, and that's not really a recommended technique I would probably stick to the first 3. Maybe I would even narrow it down to the first 2. Graphing is nice sometimes, but I'm going to go ahead and cross that out. So I suggest using elimination or substitution. In this instance, I'm going to use the elimination method. So what I'm going to do is I'm going to multiply my top equation by 2. And if I do that, if I multiply everything in my top equation by 2, my new equation that I'm going to get is 2a plus 2b is equal to 2. And then I'm just going to keep my bottom equation the same. So I have 2a plus 5b is equal to 14. And now what I want to do is I want to subtract these two equations in order to eliminate one of my variables. And in this case, we're going to eliminate a. So 2a minus 2a is 0. 2b minus 5b is negative 3b. And then 2 minus 14 is negative 12. 0 minus 3b is just negative 3b. And then from here, if I divide both sides by negative 3, I get b is equal to 4. Now, I can take b equals 4, and I'm going to plug it back in my original top equation. And if I do that, I get a plus 4 is equal to 1, and that implies a is equal to negative 3. I'm going to go ahead and clean up my screen a little bit. Okay, so this was the original equation that we were working with, and we wanted to solve for a and b. So what I'm going to do is I'm going to go ahead and replace a with negative 3 and b with 4. Those are the values that we found. And so if I want to integrate this thing, then that is equal to integrating this thing. And now I can split that up into 2 integrals, and I can also factor out the constants. And so we're going to end up getting, our final answer is negative 3 times the natural log of the absolute value of x plus 5 plus 4 times the natural log of the absolute value of x plus 2 plus our constant of integration. And here is our final answer.